Okay, now I would like to introduce our speaker today, but you know, I really don't know that much about him. I'm just really pleased that he's joining us from outside and giving us a talk. And Sarath, please explain yourself.
Sure.
and everyone else, please welcome Sarath to Edmonton.
Thank you. Thank you. So, hey, I'm Sarath. I'm a final year PhD student at University of Montreal and Mila. So, where I work with Yoshua Bengio and Hugo Larachel. And I also spend 50% of my time at Google Brain Montreal. And very soon, I'll be joining Polytechnique Montreal as an assistant professor after defending my thesis next month. So I'm in the transition period between my PhD and the faculty position. Okay, so I'll be talking about learning long-term dependencies in recurrent neural networks, which is what most of my work in the last few years is about. And 20 minutes is a challenge for me, so I'll try to give my idea as concise as possible. But just to give you a bit of background, so I work in deep learning, natural language processing, and reinforcement learning, and the intersection of all these three. But today's talk is going to be mostly on some of the work that I have done in deep learning. Okay, so deep learning has made significant progress, so I don't need to convince people now, right? So for one standard example is a single step. For example, if you take image classification, which is a single step prediction problem, right? Given an image, I'm interested in predicting what object or what animal it is, right? So in such a simple one step prediction problem, we have superhuman performance, right? We have really good algorithms, and given enough data, we should be able to get very decent performance, right? But this talk, okay, so how was that possible? So there were a bunch. I would list three major reasons. One is data, the other one is compute, and the other one is the modern optimization algorithms and standard tricks that we have developed in training neural networks, right? So okay, but this talk is going to be about multi-step prediction problem, or what I call a sequential prediction problem. So what is a multi-step prediction problem? So in this case, we are going to have some system which receives some input at every time step and makes some prediction. And let's say in the first time step it receives x1 and makes some prediction y1, and at second time step it's going to receive some input x2 and make some prediction y2, and so on, right? So the main challenge in multi-step prediction problem when compared to a single step prediction problem is the fact that your output at any time step can be dependent on any of the previous inputs, right? So in worst case, so your output yt at time t can be dependent on what the input was at the first time step x1, right? So we are going to call such very long dependencies as long-term dependencies. Okay, so now for the next 10-15 minutes, I would like to talk about this problem of long-term dependency and how can we design architectures and algorithms which can model such long-term dependencies in any sequential task, right? But before beginning, so just to give you a bunch of examples of sequential prediction problems. So the standard example is language modeling, where given a sequence of words, we are interested in predicting what is the next word, right? Or it could be part of speech tagging, where given a sequence of words, we are interested in predicting the part of speech for every word. Now, in this case, you see that it's the same word around, but depending on the context, the part of speech for this word changes, right? So now the only way to model this particular around is RP is by modeling the dependency with the previous context. Okay, so and there are many other examples like sentiment classification, where given a sequence of words, I would like to predict the rating, or image captioning, where given an image, I would like to predict a sequence of words which describes the image, right? Or machine translation, where given a sequence of words in one language, I'm interested in predicting the sequence of words which has exactly the same meaning but in a different language, right? That's machine translation. And even reinforcement learning, where at every time step you see something and then you take actions, and it is a sequential decision making process, right? So there are many examples of interesting sequential prediction problems, right? So now, given this definition of what is a sequential prediction problem and applications, so I would like to argue that we have data and compute, but we don't have good enough algorithms to model long-term dependencies in such sequential problems yet. Okay, so with this introduction, so I would like to briefly talk about recurrent neural networks in a slide, like just to set up the notations. So recurrent neural networks are the most successful class of architectures that people use for sequential problems, right? Like, so let's start with a very basic vanilla recurrent neural network, where in this case, at every time step, the system receives some input xt and makes some it's going to make some prediction, okay? But the prediction is not just dependent on xt, but it is also dependent on the previous state of the system, which is given by ht minus 1. Okay, so now u is the input weight, w is the recurrent weight which connects the current state to the previous state, and f is typically some nonlinear function like sigmoid or tanh, right? Like, so now here is a pictorial representation of the same architecture. So in this case, you receive some input and you compute the current state of the system, but the current state is a function of both input and the previous state, and then using the current state, you're going to make some prediction yt, right? So now one way to look at this recurrent neural network is to actually unroll it over time. Like in the first time step, you receive x1, you compute h1 and make some prediction. Now in the second time step, you receive x2. Now h2 is a function of h1 and x2, and you make the prediction and so on, right? So now in theory, this architecture should be able to model any long-term dependencies, because when you make the prediction for y3, it's a function of h3, which is actually a function of all x1 to x3, right? So this architecture actually has the expressive power to model any long-term dependencies that could happen or occur in any long sequence, right? Like, so that should be the case. So especially this hidden state can be seen as, yeah?
Is y3 the prediction or the target?
It's a prediction. So I'm just talking about how we use the system. Like, so you would have some target and then like you would backprop through that.
But you will have a target.
Yes.
Corresponding to that.
Yes. Okay. So one way to look at this hidden state is like this. Like, so like it's basically a summary of the entire history. Like it's a concise vector representation of the entire sequence x1 up to xt, right? Like, so now, as I said, theoretically this is a really like nice architecture. Like, so we should be able to model any long-term dependencies, but in practice, like when we start using a vanilla recurrent neural networks, like you would start like seeing that like it is actually not modeling probably not more than 4 or 5 time steps of different dependencies. Okay, so the one reason why this happens is like what is well known in the literature, which is basically the problem of vanishing and exploding gradients. So what is vanishing and exploding gradients? So let's talk about how do we backpropagate from yt through this network. Okay, so let's say I have a target at yt, like I have a target for yt, and I have to backpropagate the loss from that, right? Like, so when you backpropagate from yt, you're going to backpropagate it through this entire marked region, right? So now if you look at this, when you pass gradients, you're going to multiply that gradient again and again by this W matrix, right? Like there is this repeated multiplication or matrix multiplication that is happening when you do backprop. Also, okay, so now this is an issue. Why is this an issue? Because if the eigenvalues of W are less than 1, then you're essentially shrinking the gradient, and if they are greater than 1, then the gradient would explode, right? Like, so this is a well-studied problem in the literature, but there is a second reason why gradients would vanish in recurrent neural networks, which is kind of overlooked, is the fact that you use saturating activation functions like sigmoid or tanh, who also have this shrinking property. So every time you pass the gradient through a saturating activation function, especially when it is saturated, like it is going to shrink the gradient enormously, and like so your gradient would vanish very quickly, right? So now these are the two reasons why gradients would vanish in RNNs and makes it difficult to learn long-term dependencies. So the standard solution in the literature is long short-term memory networks, or LSTM networks, which was initially introduced in 1997, but still the de facto standard that people use in sequential prediction problems. Okay, so the basic idea behind LSTM is this. Like, so now along with the hidden state, we are also going to maintain what is called as a cell state. So now at every time step, you forget some information from the cell state, then you add some information to the cell state, okay, then you compute your hidden state. So this is like a simplification of what LSTM is doing, right? Like, so the main thing that you should look at here is the fact that you're adding information to the cell state instead of like having a multiplicative update. So we essentially replaced the additive update with the multiplicative update with an additive update, which means that there is no more repeated matrix multiplication, right? Like, so the first problem of vanishing gradient is kind of resolved in LSTMs by changing the repeated matrix multiplication into repeated matrix addition. But there is another issue that is introduced in LSTMs. So that's basically the fact that we have a bunch of gates like which are responsible for adding and removing things, right? And all these gates are sigmoids or tan H. So essentially you have added more saturating activation functions, which means that even though you resolved the first problem, you have made the second problem worse, right? Like, so that's a problem. But this problem is not visible, like if you are using it for very short term tasks like 10 time steps or 20 time steps. So the moment you start using such recurrent architectures for like 100 time step or 1000 time step problems, you would see that the models are essentially not learning long term dependencies. So that's also why it's called long but short term memory network, right? Like, so now the major issue in LSTMs is this, right? Like, so now to pass information for a very long time step, I have to essentially lock these gates, right? Like, I have to lock information in the cell so that I can use it in the future, right? So locking the gates essentially means saturating these activation functions. So the moment I saturate activation functions for the sake of preserving the information, now the gradients vanish, right? Like, there is a dilemma between whether to saturate or not, right? Like, so you have to saturate to learn, but when you saturate, you make the learning problem much harder, right? Like, so now how can we resolve this issue? So I'm going to briefly touch upon like two different ways in which you can resolve this issue. Okay, so the first solution is basically removing all the sources of saturation. So this is what we call as non-saturating recurrent unit. So where the basic idea is to observe the sources of saturation in a recurrent architecture and remove all the sources of saturation, right? Like, it's a very simple statement, but how do we do that? So, okay, NRUs are going to be very similar to LSTMs in the sense we are going to have separate hidden states and cell states, okay? But they are going to be much more simpler than LSTM in the sense I'm going to add information at every time step, okay? But now where to add information and what to add, right? Like, where to write and what to write is actually provided by gated units which are all ReLU activation functions, okay? So now I have this gate which says where to write, and there is this information producing network which says what to write, okay? So now we also remove some information from the current hidden state, which is again there is a gate for where to erase and there is a gate for what to erase, right? Like, so once I do this, like, then I compute my hidden state. So now this is a much simpler architecture when compared to LSTM, but there are some similarities. Like, for example, we have hidden states and cell states. LSTMs also have hidden states and cell states, right? Like, but the advantage here is the fact that we have additive cell updates like LSTM, right? Unlike LSTMs, like, we don't have any saturating gates. So all our gates are non-saturating, and this essentially means that in theory, like, there should not be any sources of vanishing gradient in this architecture, and we should be able to model like very extremely long dependencies, right? Like, so in the paper we actually show a series of like 7 to 8 long-term dependency tasks, like, where we show that this model learns really long-term dependencies. But for the sake of time, like, I'm just going to show one example. Yeah.
Before each ReLU, there's a unique weight matrix.
Yes. Yes. Yeah. So, but for the sake of time, like, so I'm just going to show one example, like, which is basically the classical benchmark people use for learning long-term dependencies, which is like a simple copying task, right? Like, where you feed in a bunch of information to the network, okay? So then you have a variable period of no information. You just pass nothing to the network, okay? So it could be like 10 time steps or it could be 100 time step, right? Like, so you have this variable length of no information period. Then whenever you say start, the network has to generate the sequence exactly. Okay, so now this is even though it's a synthetic task, it's an interesting benchmark, because the only way in which the network can predict this A is by learning that this A comes from the first time step, right? Like, because there is no other way in which the network can actually generate the correct answer, right? Like, so if an architecture solves this task, then we can like confidently say that architecture can model whatever length of dependency is here, right? Like, so this is a very classical benchmark which was initially introduced in the LSTM paper, but almost all the papers like which talk about long-term dependencies use this. So here is some like this is a very messy graph, but what we have essentially done here is like we have compared NRU with 10 different state-of-the-art architectures, recurrent architectures, including LSTM, and Janet, which is basically a simplified version of LSTM, which does better than LSTM, and LSTM Chrono, which is basically like the same LSTM, but with a different type of initialization, Chrono initialization. So these are all like a bunch of architectures like which claim that they do better than LSTMs. Okay, so one of the interesting aspects in the paper is that we show that like no architecture can actually be good in all the tasks. Like every architecture has its own advantages and disadvantages depending on the task. But the main result here is the fact that NRU solves the problem much faster than any other architecture. For example, the second best architecture is Janet, which takes 85,000 steps to solve the problem. On the other hand, like NRU takes only 25,000 steps. So this is a simpler task, but we also show some real tasks in the paper, like where we show that we can model long-term dependencies. So yeah.
So are they optimizers or SVG or Sequential?
All the optimizers are Adam.
Adam?
Yeah.
So like you explained, if it was SGD, like the difference would be, I guess, more pronounced, even more pronounced.
That is true, but I haven't tried it. That might be true. That might be true because so like most of the other architectures actually suffer from vanishing gradient, and in some sense Adam helps with vanishing gradients too, because it kind of rescales the gradients based on the learning, like by changing the learning rate, right? Like if you turn off Adam, then like the architectures, like the other architectures are going to learn like shorter and shorter dependencies. On the other hand, like NRUs should still learn better because there is no vanishing gradient. Okay, so then the second solution is like to design non-differentiable architectures. So what do I mean by that? So this idea is going to be based on like memory augmented neural networks, which was originally introduced in Alex Graves' 2014 paper, where the basic idea is to have a neural network access an external memory, which could be as simple as a matrix, right? Like so, and let the network read and write from the memory. So now this memory can be used as a kind of scratch pad where the network writes things and use it in the later time step, right? Like this is one way to model long-term dependencies. But the major issue with the original memory augmented neural network architecture is the fact that the reading and writing were continuous operations, just to make sure that we can actually backpropagate through it and make it an end-to-end architecture, right? Like so when you have continuous addressing mechanisms, then like if you look at the backprop equations, you can see that there are a lot of softmax and sigmoids and tanh going on, which would essentially shrink the gradients. So when you have continuous addressing, there is not much gain in learning long-term dependencies. So like the major hypothesis here is that if we can make this addressing mechanism discrete, then we should be able to lock information in the memory and use it whenever we need. And now the advantage is, if you lock the memory in first time step and use it in the 100th time step, then you can essentially pass gradients from 100th time step to the first time step without going through the linear chain of 100 to 1, right? So that's the basic idea. So just to give you a cartoonish explanation of like how such an architecture would look like. So I'm going to talk about, there are a couple of architectures that we came up with. Like I'm going to talk about one architecture which is LSTMs with wormhole connections. So I'll explain why it is wormhole later. It's not for a fancy term. Okay, so now the basic idea is this: like you have an external matrix, okay, which is the memory. Now at every time step, you receive some input and compute the current hidden state. You fill the matrix with the hidden states. Okay, so let's say in this case, like I have filled A0 with H0, A1 with H1, right? Also at every time step, there is this gating beta, so which is going to cut the connection or not. Okay, it will decide to cut or not. It's a decision. It's a discrete decision, and it is also learned in an end-to-end way. Okay, so now in the third time step, when the model computes H2, it's going to read something from the memory. In this case, it is reading H0. Okay, so now H2 is essentially a function of H0 and X2, right? And in this case, like beta 1 is equal to 0, so this connection is cut, as you can see here. But we are creating a connection from H2 to H0 because of this reading operation, right? Like so you're creating a skip connection from X2 to X0, right? So now in the next time step, the model decided to read A1, right? Now H3 is a function of X3, H2, and H2, right? So now you can see that x3 has a skip connection to, sorry, h1. So x3 has a skip connection to x1, right? So as you continue, like you're going to create dynamic skip connections because of the fact that you're reading and writing in a discrete fashion from a cell state, yeah?
So these decisions to where to write, where to read, what to write, they're based on different...
They're all based on the...
Is that true?
Yes, so the decision to where to read, what to write, and whether to cut are all functions of the current state and the input.
Right. So there are dependencies through these decisions.
Yes, so there is going to be way more linear dependencies, but I am ignoring those linear dependencies in this graph because anyway they are going to vanish.
Yeah.
So okay, so now like okay, so we are basically creating these dynamic skip connections, right? Like, so the reason why I call this as wormhole connection instead of skip connection is the fact that in the literature, like, so when people say skip connection, it basically means that you're skipping 2 time steps or 4 time steps. The number of time steps is a fixed thing. Like in this case, we are also learning how many time steps to skip, right? Like, so we also call this architecture as TARDIS in the paper, like based on the time machine from Doctor Who series. But here is a comparison between TARDIS and LSTM. In the case of LSTM, when you want to pass some information from x4 to x0, so the only way to pass information is through this linear chain, right? On the other hand, like on LSTMs with wormholes, like you can actually pass information from x4 to x0 by just 2 time steps, right? So in this case, there is a 2 versus 5 dependencies. I'll finish in 2 minutes. So there is a 2 versus 5 dependencies, right? Like, but in a real task, like you're going to have way more computational savings. So again, like, so we have a bunch of experiments to show that this is actually better than LSTM. But just to give you one experiment and conclude, like, so in this case, like we're going to look at sequential stroke multi-digit MNIST task where I'm going to feed in a sequence of stroke information to the network. Okay, so in this case, so it's dotted because it's multiple time steps. Like I'm going to give the sequence of strokes for 2 and then sequence of strokes for 3, 4, 6 and so on. So now the network has to produce the digits in the same order. Okay, so it's a challenging task in the sense, first of all, it has to learn to recognize where to chunk these sequences, and then it should learn to recognize those chunks and remember them in the same order and produce them in the same order, right? Like, so it involves a lot of learning, like when compared to like the basic copy task that I showed before. So now in this case, like we show like how TARDIS performs when compared to LSTM. So one thing that I did not describe is like we have a lot of discrete decisions happening. So how do we do such discrete decisions? Like you can either use reinforce or you can use some sort of Gumbel trick, right? Like, so we do both in the paper. But the main message here is that like we do better than LSTMs, like in modeling long-term dependencies. And like there are also other analysis in the paper which shows that like LSTMs with wormhole connections are indeed learning useful like short connections. Okay, so I wanted to talk for a minute about do we really need recurrence, but do I have 2 minutes? Can I go 2 minutes? Okay. So one last question like that I want to ask, like which I have been thinking for the last year or so, is like do we really need recurrence, right? Like so if I don't know how many of you are like DL people here, like when compared to RL, but if you're from deep learning community, like so everyone loves transformers nowadays, right? Like so transformers are essentially replacing recurrent networks in almost every applications, at least in NLP, right? Like so now the question is like, do we really need RNNs, right? Like so this was like one of our recent project, like where we did a systematic study of like comparing RNNs with transformers. Like this is a dialogue system where like we train a dialogue model which, given a conversation history, has to predict what is the next utterance in the dialogue, right? Like so we trained 3 different models. Like one is a vanilla LSTM sequence to sequence. The second is sequence to sequence but with attention, and the third is transformer. Okay, so we are not showing the training performance here. When you compare the training performance, transformers are doing better than sequence to sequence models. Okay, but we are going to look at trained models, and we are going to do systematic perturbation analysis in the trained models. Like so, one study that I show here in this slide is what happens if I truncate the conversation history, right? Like so, ideally, a good system should have an increase in perplexity, right? It should have an increased perplexity, like if it sees lesser and lesser context, right? Like so, and we essentially show that you need both attention and recurrence, not just attention. Yeah.
So what do you mean by perplexity?
Okay, so perplexity is so perplexity is like a kind of inverse of log likelihood. So essentially, like if you truncate the history, the likelihood of the next sentence should reduce, right? Like which means the perplexity should increase. Okay, so but one message that I want to say is like we still need recurrence, so they are very important. And I would like to conclude with like 3 questions that I really care about. Like, so I'm kind of using this talk as an opportunity to like tell reinforcement learning people like why do they need RNNs. Okay, so one question like that I spoke about in this talk is like learning long-term dependencies in recurrent neural networks, right? Like, so a related question like that I'm very interested in is like actually recurrent models for reinforcement learning. So as we can see, like most of the innovations in reinforcement learning in the last 5 to 10 years like are happening in the algorithmic side, right? Like when you look at the architectures that people use, it's the same ConNet which people used like 7-8 years back, right? Like so on the other hand, like if you look at the vision community, like they have gone way beyond ImageNet, right? Like so there is less architectural innovations that are being incorporated in reinforcement learning. So one thing that I would like to think more about is like how can we use recurrent models for reinforcement learning? It's not just as a memory as what most of the people use. Like the standard way in which people use LSTMs in reinforcement learning is like whenever you have a partially observable environment, like you use LSTM to just keep memory of like whatever things you have seen so far, right? Like, but we can also think about how can we use RNNs for long-term credit assignments, right? Like, so any algorithmic improvements that we have in modeling long-term dependencies should be useful in like modeling long-term credit assignments too. So like there is this scope for like thinking in both the directions. So finally, the third thing that I care more about is like lifelong learning, where like which requires long-term memory, like what I spoke about today. It also requires modular architectures, recurrence, and also like having dynamically growing networks. Like so I have done some work on these things, like, but I am just mentioning them here in case like if you are interested in lifelong learning, like we can chat about it. I'm here for the next 2 weeks. So also I'm looking for graduate students. So if you're finishing your masters, consider applying to Mila. Thank you.
Questions?
Yeah.
So you mentioned you tested it on a dialog system. So what kind of dialog system was it? Was it an open-ended or was it a task-oriented?
So we had 2 task-oriented datasets and 2 open-ended datasets. Like so it's on both types of like data.
And what was the task?
So one was I think restaurant reservation system. So and the other one was like another similar booking application.
And what was your performance metric?
Perplexity.
Yeah. So, but what was your performance metric on open-ended dialog? Because usually on open-ended dialog, people take the number of turns of conversation as the performance metric.
So okay, so there is no clear winner when it comes to like what is a good performance metric for dialog systems, right? Like so like if we start taking the number of turns, so then like we have to test it in real life situations. Like so in this case, like it's more of a analysis study. So like so we did not do human like interactions. So this is just like predicting the next utterance and like what is the perplexity. But if you want to look at like the number of turns that is happening, so probably you should deploy it in a real situation and see like what's the number of turns.
So what was your experiment setup for open-ended dialog?
It's just a language model setting. So you take the context and predict the next sentence. So given a sequence of utterances, what would be the next utterance? So that's the problem.
Okay. So basically you were not so you were not modeling the number of turns. You were just modeling the response to one.
Yes. But you will do that for every time step. So essentially you are modeling the entire dialogue, but yes, utterance wise.
So how many for how many terms did you model?
It depends on the data set. I guess like it varies from 7 to 15 turns. But then the system takes input at the word level. So it's not 7 to 15. Like it would be probably 50 to 250 words. Yeah.
On the slide where you were showing the graphs of convergence with the LSTMs with skip connections.
Yeah.
You showed that there was, for example, one of them was TARDIS plus reinforce.
Yeah.
Does that mean that you are using like
conventional gradient descent to train most of the parameters and reinforce to train that discrete addressing
Yes.
system?
Yes.
So my question is, presumably, if you took a fixed addressing system and trained the gradients, you'd get convergence a little bit. Or if you took a fixed reinforced set of parameters and trained over like gradient descent, you'd also get convergence. But if you're training both at the same time, they're kind of dependent upon each other. Did you try to address that in any way? Or
Okay.
maybe I'm not explaining myself very well here.
Okay, so when I say I use reinforced for the discrete decision parts, it's essentially like basically like now my network is a stochastic neural network, right? Like it has stochastic decisions throughout, right? Like so now I'm okay. So I haven't thought about like separating like the pure gradient part and the reinforced gradient part, but for me like so like when I have a stochastic neural network like with discrete decisions, like so I just insert the reinforced gradients at the places where there is a break, and in the beginning when there is no break you just do like regular backprop, but I'm not sure like what is the issue between these two that you're talking about.
It reminds me of like internal
There is just one gradient going to like every parameter. Like it could either come from the reinforced grade, like the approximate gradient, or it could come from the actual gradient. So like every parameter is not receiving two separate gradients.
Okay. Thank you.
Yeah.
So just to speak on maybe why we're less likely to adopt like recurrent architectures in reinforcement learning, a lot of people really care a lot about incremental updates or doing things in a more online way. And when you start introducing algorithms like backpropagation through time or real-time recurrent learning, it becomes a lot harder to think of your systems in a more online way. So I'm wondering if you know of any algorithmic innovations in training RNNs, so something more like RTRL, that is a much more online algorithm, but is less computationally expensive.
That's one of an active research areas in the sense like there are a couple of algorithms for real-time like learning in RNNs, but they are either computationally expensive or very restrictive. But I am not sure how much of a limitation that is, right? Like so if you are for example, like people still use A3Cs with LSTMs, right? Like so and people use LSTM DQNs. Like I'm not sure like if this is the real reason why. I'm not sure how much significant is this reason, like because you should be able to do learning like so even though it is not like pure online.
Yeah, no, people definitely use LSTMs, and like there's a whole line of research in deep recurrent Q networks. But I think like the reliance on the experience replay buffer to train things is another stopping point. And then how do you deal with the hidden state in those cases, right?
Yeah.
How do you initialize the hidden state in a system?
So there are a couple of works on like how can you initialize the hidden states, like so when especially like when you have a replay buffer and an RNN. So one reason why I think actually people don't pursue that line is like it requires a lot of engineering, in the sense like it's not as easy to code when compared to a plain like con DQN with replay buffer, right? Like so you have to think about a lot of issues that you would face in the replay buffer. And as far as I know, there is a paper from DeepMind like which does that, but I'm not sure if the code is out. I think it's more of a engineering blockage than like algorithmic blockage. It's difficult to implement.
So a lot of interesting things. This is a very important problem. But I'm just going to make a sort of a trivial comment, which is you talked a bit at the beginning about you used the phrase multi-step prediction, and I just want to urge you not to use it the way you did, because you used it for a one-step prediction where the guess might depend on the whole sequence leading up to now, but you still predicted only one step ahead.
It depends on the task.
But no, what you described
Yeah.
is exactly that. And I don't want to call that multi-step prediction, because there is this other important topic, which is predicting more than one step ahead.
Okay, okay,
And traditionally,
okay.
I've called that multi-step prediction. And
So can I just
your
call this
name is
sequential
fine, but
prediction?
If we take the name for that purpose, then what will we call the other thing?
Okay.
It is an important thing, predicting actually more than one step.
Okay.
You need a name for it.
So this is in between the two extremes, like one step. This is not one
It's
step.
exactly one-step prediction. You're just using a history to make your prediction.
Yeah.
Yeah. Yeah.
Okay.
Okay, so thank you very much.
Thank you.
And we should finish now, so thank you. Thanks, everybody. Thanks.
Thank you.